Okay, class 12, this is the second video that I'm posting, that after a long time. See, what we are going to discuss today basically is we are going to discuss something called, we're going to discuss parallel plate capacitors today. Okay, we're going to discuss parallel plate capacitors. But before we jump into parallel plate capacitors, let me remind you of a few things first that we've already done. Okay, like for example, if you remember, we had done something called, we had done calculations for electric field intensity at a certain point due to a charged plate. Okay, this is supposed to be a plate. Alright, so we have a plate, a charged plate of course. Alright, be it positively charged or negatively charged. So we had a charged plate, and using Gauss's theorem, we had found the electric field intensity at a certain point P, whatever distance apart. Okay, say for example distance r apart. Now what we had seen is, we had seen that the electric field intensity due to a plate, due to a charged plate, supposed to be infinite charged plate at a certain point P, is independent of the distance, and you can check that calculation, the derivation. Okay, it's independent of the distance, and it was sigma by 2 epsilon naught. Due to a single charged plate. Okay, it was sigma by 2 epsilon naught, where sigma was the surface charge density. Surface charge density meaning it was the charge on the plate. Okay, it is the charge on the plate divided by the area of the plate. A is the area of the plate, Q is the charge of the plate, so therefore the surface charge density will be charge per unit area. Alright, so we had seen this, a single charged plate we have, and the electric field intensity was sigma by twice epsilon naught. We had done this. Okay, and likewise we had done certain calculations. Okay, this will also come as numericals, might as well come as numericals. Okay, if we have done, we have done cases like this. If we have one plate which is positively charged, plus Q, say for example, with plus Q amount of charges, and we have another plate with minus Q amount of charges, and remember we had done something like find the electric field intensity at a certain point P outside the first plate, then in between the two plates at point Q, okay, and outside the second plate, okay, at certain point R. Alright, the scenarios could have been different. Maybe we had given like charges on both of the plates, okay, plus Q or minus Q. What I'm showing you here is one is positively charged, plus Q, and the other is negatively charged plate. Alright, so if this is the case like, the electric field intensity, I'm only concerned about point Q now here. Okay, I'm not bothered about point P and point R. So the electric field intensity at point Q, that is in between, anywhere in between the two plates, okay, also at point Q, will be given by sigma by epsilon naught. You can do this calculation. Okay, you can check it for yourself because we've done something like this before. The electric field, I repeat, the electric field intensity at any point in between the two plates is given by sigma by epsilon naught. Okay, so remember this, because we are going to need this when we do the derivation calculation for the parallel plate capacitor. Alright, now another thing that I want to show you is, so this is one thing. Another thing I want you to remember is, we have done a derivation. Where, or called the electric field intensity as the gradient of potential. Electric field intensity as gradient of potential. In which case we had got this expression, electric field intensity is minus dV by dr. You can go and check this again. Very, very important derivation, electric field intensity as the gradient of potential. And I had told you this negative sign has more of a physical significance. Okay, so this minus sign tells us that the electric field intensity, I have a point charge. Okay, at any point we are calculating electric field intensity, or also could be potential at certain point P, distance r apart. Okay, this minus sign only tells us that the electric field intensity goes on decreasing with distance. Okay, as we go farther away from the charge, the electric field intensity goes on decreasing. This minus sign tells us. okay, in the direction, or rather you can also interpret this as the potential goes on decreasing in the direction of the electric field. So this is the direction of electric field, in which case the value of that is, as farther apart we go from the charge, the electric field intensity and the potential both goes on decreasing. So this is one thing. So basically what I want to remind you is the electric field intensity basically is potential. dV is a certain potential, small potential divided by some distance gives us the electric field. Okay, so don't forget this. Now coming back to our real topic, that is the parallel plate capacitor. Okay, one more thing let me tell you. Say for example, we have two plates like this. Okay, one is positively charged, plus Q, and the very first video that I had made regarding capacitors, okay, if you remember, if we give plus Q amount of positive charges to this plate, we'll have minus Q amount of positive charges induced on the inner side of the second plate, and plus Q amount of positive charges on the outer side of the positive plate. So you'll have plus over here on this side, on the outer side. But once we connect the second plate to the earth, once we do this ground connection, the positive charges being free charges, they simply flow to the ground. Okay, you can check the previous video, okay, if you've forgotten this. So once the positive charges they flow to the ground, what we have is we have this scenario now. We have plus Q amount of positive charges here, minus Q amount of positive charges here, and this being grounded. All right, so this is basically this is what a parallel plate capacitor looks like. Okay, this is the theoretical picture for the to understand parallel plate capacitors. Now we have plus Q amount of charges here, minus Q amount of charges here, but still remember, so this is a capacitor now, okay, but still remember, we will say that the total charge that the capacitor carries right now is plus Q. This is plus Q, although this is plus Q, this is minus Q. It's not like these two charges are neutralizing each other. Therefore, you know, plus Q, minus Q, they cancel each other out, and therefore the total charge carried by the capacitor is 0. It's not like that. Okay, it's not like that, remember. We still say, since we had actually given plus Q amount of charges to the first plate of the capacitor, okay, this is a charge induced, this is an induced charge. So therefore, we still say that the total charge carried by the capacitor is plus Q. So if I say the charge carried by a capacitor is plus Q, you have to understand, of course, minus Q is induced on the other side of the plate. You have to understand that. Okay, now another thing that I want to tell you is, now since we have a positive and a negative charge in the capacitor, we will have an electric field that is set up in between the two plates of the capacitor, and the direction of the electric field, as you all know, will be like this, from the positive charge to the negative charge. Okay, and in fact, in between the two plates of the capacitor, I'm drawing the electric field lines to be parallel, which means you need to understand that the electric field intensity in between the two plates is uniform. Parallel electric field lines means the electric field is uniform. Remember that, don't forget. Except at the edges of the plates, of the two plates, where the electric field intensity will not be very uniform. It will be something like this. Very at the edges, it will be like this. It won't be uniform, only at the edges. Okay, so electric field intensity will be like this. This is another thing that I want to tell you. That is why I have drawn a picture over here. So this is, the heading is parallel plate capacitor. So we have two plates. I've given the first plate plus Q amount of charges. There's another other one minus Q amount of charges, induced charge. It's connected to the ground. Okay, and I have drawn electric field lines over here. Okay, except at the edges, it's not uniform. Okay, now say for example, now we give plus Q amount of charge to the capacitor. A is the area of the plate. Okay, Q is the charge given to the capacitor, A is the area of the plate. Therefore, sigma is the surface charge density of the capacitor, that is Q by A is the surface charge density of the capacitor. D is the separation between the two plates. So to say, D is this distance. D is the separation between the two plates. D is this distance between the two plates, alright? And E is the uniform electric field, the magnitude of the uniform electric field that is set up in between the two plates of the capacitor. And likewise, V. Once we have an electric field, of course, we'll have potential. Okay, so V is the potential difference between the two plates of the capacitor. So the potential difference that is set up between the two plates of the capacitor due to the two charges, okay, is V. The potential difference is V. or you can also say potential difference between the two plates of the capacitor, or you can simply say the potential of the capacitor is V. Okay, now let's get down to the derivation. Now, like I reminded you, in this case, in between two plates, okay, one having plus q amount of charge, the other having minus q amount of charge, the electric field intensity between the two plates of the capacitor is given by E is sigma by epsilon naught. So here too, in this case too, therefore the electric field between the two plates of the capacitor will be E, which is sigma by epsilon naught. All right, therefore potential difference between the two plates, let us call that V. Okay, since V, okay, so V will be E into D. Now why is this so? Because basically we know E is the gradient of the potential. Okay, so potential will basically be the electric field into the separation. So since the separation here between the two plates is D, so therefore the potential difference between the two plates of the capacitor will be E into D. Okay, I can also rewrite this as V is equal to sigma D by epsilon naught, because E is sigma by epsilon naught. So substituting for E, we get this. Therefore capacitance, every capacitor will have its capacitance. Okay, so capacitance of the capacitor, let's call that C, is charge divided by potential, C is Q by V. Okay, from the definition of capacitance, this is, so therefore C will be Q. I can write the charge to be sigma into A, because remember, from definition of surface charge density, sigma is Q upon A, so therefore Q can be written as sigma into A. So from that I have charge Q is sigma into A divided by V. Now V, as you know, is sigma D by epsilon naught, so sigma A by sigma D by epsilon naught. Okay, so sigma they divide each other over here, so what to basically get is, therefore the capacitance is epsilon naught A divided by D. This is the expression for the capacitance. C is epsilon naught A by D. So this is the expression for the capacitance of a parallel plate capacitor, or to be more precise, parallel plate air capacitor. Okay, now what is an air capacitor? Air capacitor is a capacitor in which you don't have anything else in between the two plates. Anything else meaning there is only air in between the two plates, nothing else. We'll talk about this too. Okay, alright, so this video is getting lengthier. I wanted to cut it short, so I end up over here. This is a very, very important derivation for you all. Remember, parallel plate capacitors are very, very important things for you all. By the way, let me show you one picture, one capacitor. Okay, so I have this small electronic circuit over here. Okay, these two cylinders that you see, okay, are actually capacitors. Okay, in any electronic circuits, in any electronic devices, we have capacitors like this. In any electrical and any electronic circuits, you will see capacitors like this. Okay, all right, I'll try to upload as many videos as possible from today onwards. Okay, so I stop here. Thank you.